Okay, so our last speaker today and for the whole workshop is my consultant. The blackboard.
Okay, thank you. Thank you very much for inviting me here. It's a pleasure, first of all, being back in Cortona, and secondly, at last being talking to real people, 3D people, instead of just screens or other virtual images. Before starting, I had now there is a commercial. An interruption, so we have a commercial and then we start. The commercial is that we are opening a postdoc position in Pisa on holomorphic dynamics and complex analysis in geometry in one and several variables. And everybody is welcome to apply. I will send the links for application to Filippo, and then you can send it to everybody in the meeting. And possibly some of you will receive it the advertisement more than once, because I'm going to send it to anybody you know. So, if you know your students who are looking for 1 year postdoc, please tell them to apply. Okay, this is the end of the commercial. The topic I'm going to talk today is random iteration on hyperbolic random surfaces, and it is a joint work with Artemius Christodoulou. And he is right now he is at the Queen Mary University in London. Let's start from the very beginning. It has already been quoted today, so I don't actually, well, I will write it down anyway. The starting point is a Wolff-Dejoie theorem that let me state it in this way. Holomorphic submap. We are assuming that F is not an elliptic homomorphism. Then there exists a point tau in the closure of the disk such that the whole sequence of iterates converges uniformly from compact subset to the constant map tau. One couple of remarks on the statement. First of all, if tau actually is in D, and this happens if and only if f has a fixed point, f tau is equal to tau, and it is tau is an attracting fixed point, in the sense that it attracts everything because the whole sequence converges to tau, but in particular the derivative of f of tau in absolute value is less than 1. If it is in absolute value equal to 1, then by the Schwarz lemma it is an elliptic automorphism. And elliptic automorphism are of two kinds. Elliptic automorphism up to conjugation are of the form f of z is equal to e to the 2 pi I theta z, so there are Euclidean rotations. And so we have only two possibilities. And so they can be periodic if theta is rational, or pseudo-periodic if theta is not rational? Well, pseudo-periodic means that they are not periodic, but they accumulate identity. That is, there is a subsequence at nu k convergent to the next. Okay, so this gives you a complete description of the dynamics of the submaps for the units. This has been, this morning, this results in 1926, and in 1941, Heinz gave a generalization of this kind of statement for hyperbolic Riemann surfaces. And this statement is following. And it is mostly from 1941, and there is one specification actually much later, 1988. And it says the following. So assume X is an hyperbolic surface, which means that it is covered by the unit disk, which means, well, you just exclude P1, C star, and the array. All the other Riemann surfaces are hyperbolic. Okay, let's take F homomorphic submap. Then we have substantially four possibilities. The first case is F as an attracting this point. Let's call it so next, and this means what I wrote here is a fixed point and the negative modulus less than 1, but in particular this means that the whole sequence meter is converges to this point. So the second case is F is a periodic automorphism. Well, it's periodic, so the dynamics is trivial. The third case is F is a pseudo-periodic automorphism. And this actually implies this can happen only if X is D, the point of this star, or anomalous. And so essentially they are just a rotation again, so they are in the same position over there. Or the fourth case is that the sequence of iterates is compactly divergent, which means essentially it's going to infinity. Somehow on complex sets, if you want a more precise definition for any k and h in S compact, there exists mu zero such that f to the nu of h in the set of k is empty for any nu greater than mu zero. Actually, this statement here is not very difficult, not completely trivial. It needs some, but it's not really deep. The biggest part, which is, we can say something more here when our hyperbolic Riemann surface, instead of being just an absolute Riemann surface, is actually inside the larger Riemann surface, so we have a boundary. And indeed, the statement is if x is contained into Xf, that we can say that it is a compact in a surface. We are not assuming anything, it's not necessary hyperbolic, just to have if you want an Euclidean boundary. And the boundary of x in x is nice. Well, there are several possibilities, but let's say, for instance, that the boundary of x is the union of Bertrand curves and isolated points. And this happens to the domain in C, that is a projected plane, whose boundary are finite number of Bertrand curves isolated points. There are also some more general things. Then, in case 4, implies that the sequence of the sequence of levers is converted to a point in the boundary of x, exactly, and so happen in the next. Since this morning, we talk about compactification, several kinds of compactification, actually, there are a number of intermediate results between this one or this one, and what kind of compactification to consider for x. So, different. But for our way, this is what I want to do. Okay, so this is a crash course on iteration and hyperbolic surfaces on the variable. Let's say what I mean by random iteration.
Marco,
Yep.
if your surface is simply connected, so clearly it's polymorphic to the disk, but it's not obvious that you have the last statement, but I think it's fine at least if it is a domain in the Riemann sphere, right?
Now, there is a, even if you take the simply connected domain that you check any comment surface, as soon as the boundary is nice, for instance, the boundary which overlaps, then this is true.
No, but I mean, the boundary of a simply connected domain can be worse.
Yes, yes.
But
the boundary, if a boundary, you can have a simply connected domain with boundary which is terrible, yes, and then this is not necessarily true. You can discuss it.
Yeah.
That examples of
I mean, it's clear for semi-groups, but for just hybrids of one function, well, we discuss it.
Okay, so what is random iteration? Actually, random is just a catchy word, as you see. It's not really what it is about. But I wrote here the iterative function without comment. The iterative function nu just f composed with f nu times. Okay. Well, random iteration. So this is standard iteration. Is when you replace, instead of composing with itself always the same function, you compose different functions. And in particular, you have two different ways of considering this kind of iterations. You can define, let's call it mu, where you start from x0 from over here, and then you apply different function on the left, and then you can use R where you do the same on the right. Here, we just one, 2, 3, here. concerning well, discussion with you, it's definitely not decided in the literature whether we should start with 0 or we should start with 1. Okay, the results are the same, but the notation can change. So, okay, this kind. So the idea is that you have a family F nu of holomorphism of maps of this algorithm surface X, and you want to know what happens to the sequence F nu of L when you go through the thing. Well, if you think stated in this generality, the answer is anything can happen. Just think what can you do when you take as max constants. If you take constants, mu is a constant sequence because F0 is the one dominating everything. And mu instead it changes at each step, so you can get any kind of behavior. So this question becomes more interesting when you specify a way to choose this family, not a generic family of submaps. Random in the title comes from one source of idea that of reason we some people start thinking about this kind of sequences. Which is you choose randomly the exact functions according to some probability measure which is concentrated nearby a fixed function. Because one of this problem started in the 80s. And one of the reasons to study this kind of sequences is when you want to simulate a dynamical system inside a computer, you have to approximate. The approximation can change from one step to the next, and you might control the error with some sort of probability distribution. And so you have instead of you want to simulate standard iteration, and what you're actually doing is composing maps of this kind, where the changes randomly, but there's some distribution. Another source of problems of this kind, again in the 70s and the 80s, is the theory of continued functions. Where instead of just the standard situation, you have just to have the iteration of the Gauss map, they started iterating on mixing different kind of functional linear functions. And so there are a number of problems on this. In this talk, I'm not going to use the word probability anymore. I'm not interested in that kind of approach. I'm interested in two choices of this family. The first choice, one, is we'll take our final at mu, which is holomorphic maps from X into omega, where omega is a subdomain of X. And well, the word I'm going to use is a block domain. And well, I will give you the definition. The easiest case is when omega is relatively compact into X. But actually, there are block domains that are not relatively compact, so it's much more interesting. And the second case is when the F nu are close enough to a given capital F or not a certain type of X input. For instance, we can assume that in some cases we will assume that the F nu converges to F. And an interesting part of this part of the story, as we'll see, that the results will depend on how fast this sequence is convergent to F. And there are some interesting kind of results. Okay, so let's start with part one. It is blocking mechanism. I should immediately say that the definition of block domain which I'm going to give and the complete study of what happens for this kind of sequences is due to in 2004. What we did was to complete the results for the case of the left sequences. And I will comment a bit on the history. So, what is a block? Definition, let's say X hyperbolic on surface, denoted by omega x with Poincare distance. And also denoted by dx of zr. This is the Poincare ball center. C and X correctly radius. Okay, and well, the Poincare distance is just to obtain, you take the Poincare distance on the disk and you project down using the universal product. And it has all the decreasing properties we are used to have in the Poincare distance, the Kobayashi distances. In particular, if omega is contained in X, then the distance, the Poincare distance on X restricted to omega times omega is less than or equal to the Poincare distance of omega. So in some sense it makes sense, because they are different, to consider the Poincare balls for the Poincare distance in X central point of omega. And so they defined the following number R of omega X, which is the supremum of R greater than 0, such that the resistance Z in omega, that the Poincare ball in X or Z, center Z radius R is contained in omega. And we say that omega is blocked in X if this number is finite. Okay, so if this domain omega cannot contain balls with respect to the planetary distance of x, smaller than omega, larger than a given radius. Examples, well, one example is very easy. So omega, if omega is relatively compact in x, then clearly omega is blocked. Because if you take a closure are a finite diameter, and so it cannot contain balls larger than that diameter. But there are other examples. If you take a sequence Z nu, a sequence in X without accumulation points and intersecting all balls ZR, a fixed R. Well, since it is without accumulation point, it is closed, and if you take as omega x minus this sequence, this is clearly blocked because you cannot have a point from any balls of this vector, so there is no way. And another example which I found particularly amusing, based on the taste, is that Stokes domains in D are what? Essentially because you can build them inside a union of balls of the same or fixed rate with the center. Anyway, there are examples which are not relative. The main result that Burton, Karma, and Minden proved is that when you study, well, when you have holomorphic maps from a domain into another, holomorphic maps we know that are weak contractions with respect to the Poincare distance. When the image is a block domain, you have something better. So I use now, if omega in x is blocked, then there is number r between 0 and 1, strictly less than 1, such that omega x of z and w is less than or equal to L times omega x CW for all Z and W in X, and for all F and X in omega. Okay, so maps with the image in the block domain are strict contraction for the Poincare distance of n space. And then, well, the observation that Burton and company did is that if you want to study the sequences LU and RU in this setting, it's suffices to study what happens when you have a straight contraction of a metric space.
This is because it's block means Lipschitz, right? So the metric is.
Exactly. The proof is that from this, you can show if you take a quotient of the Poincare matrix between omega and x, this quotient is bounded by a constant strictly less than 1, and then integrating curves. Okay, so result is the following, which is again Burton et al. For the right sequences. For some reason, they were interested in the left sequence or something. I'm pretty sure that they couldn't prove, they could prove what can stay here. So, but in the literature, there is nothing. So ours. Because now it will go to archive, I think, next week.
I think Marco, I think actually a proof for the other. I have a paper where I extend this theory for strongly complex domain.
Yeah.
More or less, and I think that there is that.
Yeah, yes, in general, some instead of variable, but
Yeah, I think it's easier the left than the right.
And actually, I should say that there is work by Gill in around the 80s, and well, you can find a number of his preprints up to now. He worked only in the disk with too many hypotheses, but essentially the idea of a proof statement is nothing really deep here. Anyway, the statement is the following. If you take a sequence of continuous maps of X, D here is a metric space, and we are assuming that the F nu, let's put it this way, are sheets that is they satisfy basically over here. For some one. Then the following things. First, every pointwise limit, or if you want to say a connection point, of L and R is constant. I'm not yet saying that they converge, but if you take a subsequent conversion, the conversion necessary to constant. They are contracted, cannot say nice actually. Second point is that let me put it this way, pointwise convergence implies convergence of uniformly and complex subsets. Or what is set in comes from free in this case. You can prove it, and it's comes from free to lines. And free, let's assume that xt is complete. As it happens in our situation. In particular, since it is complete and this is a strict contraction by Bach theorem, this implies that every f nu has a fixed point. If you don't know what to assume as the complete, assume just that every f nu has a fixed point. Then, what happens is that the sequence, the whole sequence of the left positions converges to the point in x infinity next. If convergence should converge to a constant, so convergence to x point, if and only if the sequence of the fixed points converge to x. So you just check what happened to the fixed points, so you get the behavior of the sequence. And fourth, again, assume x is complete. This time, if there exists an x naught such that the sequence at mu x naught is bounded, then the whole sequence of the right compositions converges to a constant. The constants may have anything to do with the x naught or fixed point, because if you just change the first man in the sequence, you can change the limit. But it converges to a constant. Okay. Well, in case 3, we have an if and only if. In case 4, there is only if, because the only if is false. Example. Okay, let's do it this way. Let's say x equal to b omega eg block not relative contact, for instance, false region, and assume you have a sequence d mu in omega with c mu converted to the boundary of b, to the point of the boundary. So let's find the universal cover. Several non-examples in this theory are constructed using universal covers with time mu of 0 is equal to 0. And then put as f0 0 and f mu is pi mu minus 1. Okay, so what happens with the real observation is that then the sequence at mu of 0 is not bounded because it's sequence 0. But mu is identically to 0. And then you put the first net is a constant, whatever happens afterwards is irrelevant. Okay, so it's not possible for infinite. Possibly there is some space here to understand what happens if you exclude the constant x from the family. Another observation I will make of this, and then we'll move to the second page. So that will go fast. Is well, we said that if it's block, then we have this wonderful estimate. Of course, this is only an if. It is not an if and only if. But block domains are close to be optimal for respect to problems because of this proposition due to Kim and Lattice 6. Which says that omega in G is block if and only if. So I mean F mu contained in all of D omega, the right sequence mu as only constant accumulation point. Okay, so if you want to have something like that, the first one you essentially need to be in a block domain. There is not a problem. No, actually, it's not another problem. This is false if x is different from b. More precisely, there exists a counterexample. There exists an x which is not d, where you have an omega, so that all this happens, but omega is not wrong. So there is again over there is voltage. Okay. So let's go to the second part. That is when you have a fixed capital F holomorphic of map of x into x, and we have a sequence f nu closed. V case x equal to v is due to it is 2019. It is still an archive that has been accepted, it's not yet here. And what we did is essentially to generalize and take care of some particular cases, different cases to hyperbolic surfaces. So, if you remember Heinz' theorem was written there, we have essentially three cases to consider. When the f, or let me write it down here a second. Yeah, capital F, not some map of x, and f nu closed in some sense. So we have three cases to consider. The first one is when capital F has an attractive fixed point. The second case is when the sequence of integrals of capital F is completely divergent. And the third case is when capital F is a periodic or pseudo-periodic automorphism. So let me state the results, and then, depending on how much time I will have, I will show you some examples, maybe time, very fast idea of a two-show route. So here one. This is the case F as an attractive fixed point. What we have in mind is that somehow the dynamics of F should force or guide the dynamics of the sequences LU and RU, and this is true up to a point. So in this case, for instance, we can see that there exists a neighborhood U of F. This is a neighborhood in this the space of holomorphism map of x into itself with respect to the content of the topology of convergence, such that if you take the FU inside this neighborhood, then the sequence, the right sequence, mu converges to a constant. But we cannot say it converges to Z0, because again, just changing the first mapping can change the limits. The second case for the mu, well, this is not enough. You have to require that the sequence of mu converges to F, and the sequence of left compositions converges to the same fixed attractive fixed point. Okay, and there is an, if I will show you, there is an example saying that in case 2, requiring that f nu is contained in some neighborhood u is not enough. Okay, you can take this neighborhood as small as you want. You can find functions inside there so that this sequence gives something. Okay. Theorem 2, which is possibly the most interesting, yes, the most difficult to prove, is the case when the sequence of vectors is compatible with vectors. Well, as I will show you in a minute, in the case, there is nothing, at least we don't know how to say anything about the right composition. But on the left composition, we can say, essentially, we to get what we wanted, it is not enough, well, it's clearly not enough just staying inside the network. It is not enough just to convert to F, we need to convert fast to F. More precisely, there exists a sequence U nu of neighborhood of F, of capital F, such that if F nu belongs to U nu rho nu, then the left composition sequence is compatible with each other. Moreover, actually, as soon as one has this, then this consequence is easy. If the original sequence converges to a point tau in the boundary of X, for any reason, doesn't matter, just you know that, then also L nu converges to the same point. Okay. Let me give you 2 examples to explain why we cannot use well. First, yes. It's a very fast example showing why you cannot get some anything from an R sequence. And the example is the following. Okay. One, let's say X after of thing. Let's say capital W is W of 1. Everything is correct. Let's say F0 of W is I plus e to the 2 pi I z. And if you do some computation, you see that this map is a subnet of H plus. And of course, when you compose it with capital F, you get something.
Z is W, right?
Z is W, right? Yep. And then you say mu is equal to capital F for mu equal to lambda. Okay. So, well, clearly, F mu converges to F as fast as possible. Okay. So, not possible faster. And, well, R mu is an integral F0. Okay, it converges really, but to something which is definitely not materially divergent as it's so we cannot get a result of this kind. Maybe there is something else. The second example is to show that we need a control on the speed of convergence of f mu toward to f. I didn't write it down because it's not necessary in the statement, but clearly this sequence of neighborhoods is closing down f. So being inside there implies that f mu converges to f. But they should converge very fast. And let me give you this example. Okay, let's take again x plus. In the original paper by Short and Alfiers, there was one line saying that it's very easy to build a max with the diagram of the sky. I spent 2 days trying to build this map without succeeding, so I wrote the revision we started already. And the answer a week later saying, well, yes, actually it's not that easy. And the example requires to find gesture computations. But the idea is essentially the following. Let's say capital H mu is w minus 1. The definition is correct. Let's say G W less than 9 this way. Mu square plus mu plus 1 w minus mu square over w plus mu square minus mu plus 1. Yes, this is actually, it turns out to be a parabolic automorphism fixing the point mu of the boundary. Okay. And notice that this is actually a difficult part of the stuff. That G mu converges to F when mu tends to infinity. So, well, the idea is to build F mu taking alternatively longer and longer sequences over copy of F and copy of G with new pointers. Essentially, what we would like to do is the following. It's easier to make a drawing. Only to the right. Let's put it over here. Okay. So we have I over here. So what happens is that G mu is a parabolic automorphism with fixed point mu. So if you iterate enough, you can take any point and bring it as close as you want to mu. On the other hand, f is f w minus 1, you can take any point and iterate it. You can get it as close as you want to 0, at least as a real part. Okay. So the idea is instead from I, you iterate enough time G mu, so you go close enough to mu, there are of course a number of estimates 1 is to 2. Then you apply F enough times, so you get somewhere over here, close to the origin. And then you repeat the argument with mu G plus 1. So now you use mu plus 1 here. So we take mu plus 1, mu plus 1 to go even closer to mu plus 1, and then you use F again to come back even closer to the origin. What happens if you construct a sequence mu so that mu of I accumulates zero magnitude. And then this is not a problem, because of course this example shows that if the sequence is convergent to F that slowly, so it means that it gives to a counterexample to the second part of the theorem. But this sequence here is still compactly divergent, so there is an open problem where we can construct a sequence of F nu convergent very slowly to some F, so that the sequence F nu is not compactly divergent. We try evidences now. Okay, last statement, and then close. What happens when you have F is a periodic of automorphism? But the first part of the statement is that studying S about G is equal to G is enough. Because in most cases, if you take and well, let's say this and let's say we have a few convergent class. Well, in most cases, the only way a sequence of certain map can converge to another model is when it is equal to the so you can get rid of the most of them. And the other case is F essentially is a rotation, and then you are essentially the list. And so we can just go to a short video speed in 2019. And again, you need to have F nu going to have faster enough, and faster enough means the following. There is A different from B and D. There is A different from B and D. Now let's call it A1 and A2, so I write only one series. So that the series from 0 to infinity of omega F nu Aj J convergence of J from 2. Actually, they prove that if this happens from 2 points, then it happens to all in all points. And this is important to prove. Then, what happens is that capital F minus mu composed with A mu and capital F R mu composed with F minus mu converge to a non-constant model. So in particular, when F is the identity, you get a convergence of both LU and R. Okay, I think yes, my time is essentially up. So I stop here. Thank you.
Questions either here or well, one question is, I don't know, maybe it's the way you define this set U, so I don't know. But what if you know that your capital F is image in a block domain? Then which kind of result? You have something better or even more?
Well, actually, the block domains enter into play in theory. Theorem 1 essentially you show that under this condition you can have these maps of the image in a block domain, and then you apply the privileges. In the other cases, no, it's a completely different approach. But in theorem 2, the big part of the story is to understand how to define these neighborhoods so that you can control everything on the disk. And so you need essentially a sequence of compacts exhausting the disk, and you have to find points inside this compact so that you can cover with bolts, and then you take an intersection of the typical open neighborhoods on this, and then you control it. And this also is more complicated than it seems, because well, as I told you, there is a result saying that if you have a control of 2 points, then you get this on all points. And this is essential in controlling what happens in disk.
And then probably you already thought, what happens if you compose your G nu with an hyperbolic automorphism having the same fixed point and taking also some the boundary relation coefficient so that you
I tried out, but I tried one day, not too much. I tried, and well, when I tried, either I get lost for this, or I couldn't get I needed a fixed point, and here I'm going to fit. I always lost one of the properties, but of course, this doesn't mean that it doesn't work. I just tried one way.
If there are no other questions, then thank you.